I'm Samuel Como, and I've been part of VCF networking group for almost 8-9 years now. And performance is one of my focus areas. Before VMware, I was part of VMware Broadcom. I was also part of Cisco, and there also it was performance. And my focus is more on application-based performance and how that translates, right, like from a networking perspective. Now, today I'm supposed to be presenting with Andre, and Andre had to take off those. So here's the deal, okay? Since I showed up, any bad reviews goes to Andre, okay? Not to me, please, okay? All right. So let's start with the disclaimer. I mean, there may be things that are like future-looking and so on. So by now, you probably have seen this several times. So please pay attention to that. Okay. From an agenda perspective, we'll take a quick overview, and anyone who has attended or seen some of the performance sessions in the past, you might recognize two slides, the first slide and the last slide, okay? This is just to set, just to make sure that we're all on the same page when we are going through this content. And then after that, like we look at enhanced data path standard. A gentleman here was asking, like, what happens with this data path? Where do I use it? Where shouldn't I use it? And so on. And those are some of the things that we will touch on. And we'll close with some monitoring-related tips and also some SmartNIC-related details. And that's about it, okay? We may or may not have time in the end for questions, but I'll be here, though. And please feel free to reach out. Also, since it's actually a much smaller group, if there's a question that you can't wait till the end, please feel free to ask, okay? So I don't mind at all, but yeah, please feel free to ask. Okay, let's start with just a baseline, right? What is VCF networking? What is NSX, right? When you have two ESX hosts with a couple of VMs on that, and you want a connectivity between them, right? In the NSX VCF networking world, this is what we call the segments. And when you want these segments to basically send traffic to each other, right? So the way this process happens is the VM would send the traffic down, and somewhere in the ESXi stack before handing it over to the PNIC, and also within the PNIC stack, okay? You have encap and decapsulation happening for this traffic, and then that traffic is routed across to wherever the receiving ESX host is. And then again, at that PNIC layer, and also within the ESXi stack, right at the, the beginning part of that stack, you have a decapsulation or encapsulation based on the direction of your traffic. And then the traffic is sent to the VM. It's the same path, even if you go with something like routing. Let's say you have VMs on two different logical segments. In the VCF networking world, you have something called logical routers, which are distributed, actually. And these routers, they make their decision on the source host. And once those decisions are done, routing decisions are done, it's basically the same path. You again encapsulate, send it across to the other side, and then decapsulate on the other side, and send it to the concerned VM. Now, all of this is what we call the east-west traffic. That is traffic within the NSX domain. This is within the ESX host within that domain. And sometimes the traffic could be within the host, too. So all of this traffic leverages certain features, like, for example, the TSOs and LROs. We'll touch on it briefly. If you want to go into the details of this, then we have a design guide. If you search for NSX reference design guide, the performance section actually goes into the details of what all these different tuning parameters are. But I'm here to tell you today, like, you don't have to worry about all of that, okay? So if you want to read, if you want to learn a little bit more, then that's one place to go. Okay. When traffic needs to exit the NSX domain, this is where we have what we call the north-south traffic patterns, where the encapsulation and decapsulation happens on the edge node in this case. And the edge node could be running not just routing, but several other services too, right? And can be used as your perimeter firewall too. And in this particular case, instead of the encap decap happening on the ESXi host layer, it actually happens at the edge layer, and then the traffic is routed out. And when it comes to the edge, you have two different ways to do this edges. Like you could go with a bare metal edge, or in this particular case, I'm showing you what is a virtual machine edge. And you have several form factors within that virtual machine edge too, in terms of how many CPUs you allocate for these edges. And when it comes to tuning here, you're looking at queuing and features like DPDK to help with high performance on the edge side. So that's basically what VCF networking is from a performance perspective. And some of the things that people get concerned about is like, this whole encap, decap, which is actually to a large extent offloaded to the PNIC. That is, the NIC card actually does most of the heavy lifting for this overlay stuff, right? So most of it, it doesn't really impact the system at all. Okay. Application types, again, a baseline here, and then we'll move on, right? So a baseline, there are two types of applications generally. Some are large flows and some are small flows. The large flows, of course, they are bandwidth hungry. They can take up as much throughput, like, if you have a 200 gig NIC, they'll end up using the whole 200 gig NIC. Now, the thing about these large flows, though, if they are delayed by a few seconds, nobody cares, okay? So, and then you have small flows which are not the same. With the small flows, you have to be like really sure, especially on the latency side, to make sure you're not increasing the latency and so on. In fact, like we were having a discussion just yesterday on, some latency happening somewhere. And when you think of the entire traffic path, right? That latency could be from anywhere from the virtual to physical infra, and you need to basically look at every single point. Buffers, which are supposed to be really, really good, they can increase. Back in my Cisco days, we did some tests with buffers, like really large buffers, and they can have a huge impact on latency. So latency can be everywhere, anywhere, and that requires a little bit of making sure, your entire path is clear. But they are more latency sensitive, so large flows and small flows, right? The requirements are different between these two, and small flows are the ones that are more critical generally for a business perspective, not the large flows. Okay, last one. From a performance considerations point of view, right? The current data path that we have, the standard data path that we have, it is tuned to help with large flows, and there's a reason why. The reason is when you're looking at these packets, you're only looking at the header, making the decision, and punting the packet off. And in that case, the larger the packet, the less work that you do, right? And so for whether you take switching, routing, whatever, right? All of these are just looking at the header and making that decision. And that way, it helps a lot from decreasing the CPU cycles on these workloads. With that baseline, okay? One last item. Over the years in the past, we've looked at how you have to tune these workloads, right? And some of the things that we've looked at, one of the easiest hacks to maximize throughput is Jumbo MTU. This is across the board, virtual, physical, whatever you take, right? If your workloads can take advantage of Jumbo MTU, then this is the best way to go because you're passing a whole large payload across and you're done with that, right? Now, if you don't have that, if Jumbo MTU is not an option in your networks, then the other way to go is to use something what we call TSO, where a large amount of data, when you're sending it out, you basically pack it within the system. It can be as large as 64K, not just 9K, right? 64,000 bytes is what you're processing with every hit on that packet header. And then the PNIC, the NIC card actually takes care of sending that traffic out according to your MTU definitions. And the same thing on the receive side, that's on the send side. On the receive side, you have something similar. And as long as packets from a same flow show up as a cluster at the same time, then you're able to pack them together. And this one generally is about 32,000 bytes, but you don't even hit that 32,000 bytes because there's a whole bit of a dance here in terms of, I don't want to wait forever and increase latency, but I don't want to pack the packet going if it is too small too. So there's a little bit of juggling to get the right size, and then you send that up the stack again. All of these help if you see with large flows. Our problem has been for since inception almost, right, is what do we do with a whole bunch of all kinds of flows that show up? What do you do with this, right? And this is what I'll be focusing on for the rest of the session. Almost the main part of it is going to be focused on this. What do we do with this diverse flows? So, enhanced data path standard. This is not really a new stack, but based on what we've seen with the standard data path that we have today, we started trying to figure out how do we improve for these diverse flows. And the enhanced data path stack, enhanced data path standard stack basically helps you have high packets per second rate and reach line rate with efficient CPU utilization. And we'll be looking at all of those metrics shortly. Okay, how does it do that? We took the best parts of our current stack. When I say standard data path, all of you who have deployed NSX, if you've not heard of enhanced data path or if you've not clicked on that option, you're on the standard data path. And the way the standard data path works is interrupt driven. That is, cores are allocated when you need it. Otherwise, they are used for the workload. And that's a good thing. But because we are not able to use that data path for workloads that are really packet centric, like telcos that gentleman here was talking about, we came up with enhanced data path performance mode. This was designed for telcos, but the caveat here is you need to define how many cores you want to allocate for the packet processing. And this is one time, when you configure, this is one-time decision. Of course, you can change it later, but it's not dynamically changed. And once you set, let's say I want to use 4 threads, then you are stuck with this 4 threads. And it's not just the 4 threads, but it's actually the physical cores. So if you have your hyperthreading enabled, you're burning both of those threads too on that core for packet processing. And while this is good, it's not good for the enterprise because in most cases, you don't know what you need. And so what we've done is basically taken the learnings from both stacks, the current stack and the stack that we've been using for, again, almost 6-7 years now at the telco front, and basically bring those learnings down into this enhanced data path standard where the packet representation is completely new. It's brand new. And then you have much better CPU utilization here and so on, and we'll go into the details of how. All right, so 3 main components that make this the heart of the enhanced data path standard is one is a completely redesigned packet representation that's almost half the size of what we have today, and that by itself optimizes the performance and the CPU utilization on these packets. And second thing is what we call thread load balancer, and we'll dig a little bit more into this to kind of understand what that is, and then an enhanced way to look at the flow cache too. Thread load balancer. So in this new enhanced data path standard, the way we are looking at the threads is when you bring up the system, it comes up with a certain number of threads, about 16. And the system actually monitors these threads on a continuous basis. When traffic shows up, you start using these processing threads. And because the system monitors it, if there's more traffic and that thread can take on more traffic, that's actually sent to the same thread again too. till it hits a high mark. Once it hits a high mark, we start creating more threads. And this basically allows us to optimize how these threads are used for packet processing and also dynamically create this stuff. Now, it's not just, and this cycle keeps going on, but it's not just that we are monitoring the threads themselves, but the entire architecture is actually NUMA aligned by default. And so we try to keep track of the VMs and then the threads within the same NUMA, and so you avoid all this inter-NUMA communication and those boundaries and those checkpoints. And it's the same thing on the NUMA 1 too, the same process, multiple threads on the other side too, and they basically are monitored throughout too. Apart from that, we also have what we call flow cache is another really old system, right? Like it basically helps you improve the packet processing speed because you've already made the decisions and you're just looking at the hash table to punt your packets across. And what happens here is just a brief intro, slow path, like the very first packets, they'll hit the slow path, the decisions are made, and once those decisions are made, the flow cache table is updated, and the rest of the traffic is going through the fast path here. We have flow cache both coming into the system and also going out of the system, and this flow cache is actually per thread. So it also avoids some locking contentions and stuff like that, which was part of the problem with the current standard data path. With these three are basically the main core elements that help you get this high performance with the enhanced data path stack. With that, how do you enable this mode? Before enabling the mode, one of the things to really take a look at, most of the problems that we come across with the current stack, especially, right, like, and it's true for the enhanced data path standard stack too, is confirm whether your driver and firmware is actually on the VCGIO list, okay? This is a key piece. You're looking for what we call enhanced data path interrupt mode. And in this case, I took Broadcom and basically looked at, okay, what drivers are available. And once you open the top, you can look at enhanced data path interrupt mode because the CPUs are allocated as needed. So that's what you're looking for here. By the way, most of these slides are kind of like a reference for you, so you can use them later when you're looking at these stuff, right? And you use that and basically make sure the driver and the firmware actually match what you have, both driver and the firmware. And most often what happens is we keep updating the drivers, but the firmware remains like, 3-4 year old firmware or whatever, right? So those things need to be updated too. And there's a different path. Each vendor has their own way of updating those firmware. How do we enable it? For VCF customers, by the way, how many of you are like VCF customers? Okay, using SDDC Manager? Yeah, okay. If you're using the SDDC Manager and you're deploying a cluster, you would see this new option. This has been around maybe for the last 1 or 2 releases now, I guess, 5.1, and then of course 5.2 definitely. And you're going with enhanced data path interrupt mode, not enhanced data path, not standard. Standard is the default. By default, if you don't make any changes, that's where you would land. And this is a cluster-wide configuration. It would apply to the entire cluster here. And you have an API method too to actually enable this. If you're more comfortable going the API route, of course, you can do that too. Okay. On the NSX side, how many, I guess the rest of you who are NSX users are probably on this side of the house. On the NSX side, you have this ability to change it at the transport node profile area. So you can basically make that change. And again, here too, you would see enhanced data path standard, enhanced data path performance. The performance is basically if you know exactly what your traffic pattern looks like, right? Which basically means this is the friend here was asking like, okay, what does that look like? I know my traffic is, for example, HFT kind of space, right? 256 bytes coming in at this particular interval, every second I get these many packets, then you can really define, okay, how do I allocate the course for that, right? If that's not the case, most enterprises, almost all of you here, except for folks who are really into that telco world, if you don't know, by default, just go with the enhanced data path standard mode, okay? All right. Again, there's an API call too, if you want to enable it instead of going the UI route, there's an API way to do this too. Remember this interrupt and standard, they're the same. Interrupt meaning it's interrupting the CPU to get its job done, not poll. Okay, how do I know whether it's enabled? In this particular case, if you look at the two VNX where this is enabled, you can just go and look at ESXCFG-ENX, and then it would tell you, there's 4 different columns here. It tells you whether it is available, and it tells you whether it is enabled, right? ENS capable, and whether ENS is that's enabled. On this particular case, for the Mellanox NICs, where we have the stack running, that's where it is enabled. But if you look at the rest of the stack, that's not enabled in those cases. And it's the same thing with interrupt, INTR, interrupt, that is the enhanced data path standard mode. You can confirm, okay, fine, this is actually running in the standard enhanced data path standard mode. All right, here's the question that you were asking. So standard data path is where you're at right now, which is most often, which is really good for large flows. But recommendation is try implementing enhanced data path standard mode, which is good for both large and small and diverse type of flows. When it comes to enhanced data path performance, you really need to know what your traffic is. So you need to know what your traffic is, and you should be able to figure out how many CPUs do you actually want to allocate for this. And I have a slide on this later on too that kind of describes a little bit in terms of why that matters. In terms of CPU allocation. Let's look at a little bit at the performance results with enhanced data path. What we've done is, this is with VCF 5.2, and that means the ESXi 803, NSX 4.2, and Mellanox NICs, and we're using Ixia for this testing. Ixia, because it enables you to set the test with a certain drop rate. In this particular case, we're looking at 0.001% drop rate, which is almost nothing. And these are the results with that. The way it is set up is pretty simple. It's an extra large edge VM. And we're using 100 gig NICs in this particular case. And again, the packet rate is, drop rate is 0.001%. One question here, right, before I continue. Excel HVM, multiples, I think a few of you were saying, how many of you have edge, use edges, overlay and edges and so on, right? And do you use medium, large, okay, extra large? Yeah, okay. So, how many of you have tuned the extra large or large edge VMs? No? Okay. There's a bunch of tuning that happens. On the standard data path, if you want to get to the numbers that I'm showing you for standard, the current data path, you have to do a bunch of tuning. Just look up my name, and there's a blog on that in terms of what all you need to tune both at the ESXi layer and at the edge layer to get the best performance out of it. But when it comes to enhanced standard data path, you don't need to do any tuning. The results that I'm about to show you, it's all without any tuning at all, right out of the box. The only piece that is different is NIFC is disabled. And I would recommend that both for enhanced data path standard, and also if you continue on standard data path, that's one of the things that you might want to take a look at and disable that when you have edge clusters and so on. So, what does the performance look like? Let's take an easier one. This is the throughput. You're looking at green is the enhanced data path standard throughput. Yellow is the standard, the current data path throughput. That 34 gig, by default, you might get about 20, 25 gig. That 34 gig is because there's a whole bunch of tuning that went into it to get to that level. The 64 gig, there is no tuning at all. And this is with a single edge VM. When you have two edge VMs, of course, it goes beyond that 100 gig, right? So, and this is true across the board, except you might notice the 64 bytes is not the same case. Most enterprise workloads, what we see is between 700 to 800,000 bytes is what you would see in enterprise workloads. But with telcos, that's not the case. Voice over IP, if that is all that you're running throughout the day or in your clusters, right? Those are different. So that's where, if you have like really, really small packets and that's all you got in your data center, of course, in performance mode might help in those cases. But for everything else, for typical standard enterprise workloads, enhanced data path standard basically shows you much better performance. And especially at that 768 bytes, if you're looking at 25 gig ports, you're basically at capacity with those ports. By the way, these numbers are conservative. I have a small demo later on too. I think we have time for that. So you can see what the numbers look like. So let me embed the PPS on top of it. The lines that you're looking at, the blue is enhanced data path performance packets per second, and then the red is the standard data path. And as you can see, there's again a huge difference. It's almost like 50 to 70% improvement when you go with the enhanced data path standard, and it already hits your line rate limits, so even with a single extra large edge VM. CPU utilization. This is another thing that I was talking about in the beginning about how it is optimally used, right? So the blue here is the enhanced data path standard, and then the red line on top is the standard data path. You basically are using almost half the cores, but you're doing twice the work. A better way to, it may not be easy or apparent to see what the difference looks like. The better way to look at it is per CPU, what is the throughput that I'm actually achieving? And when you look at those numbers, this is what it looks like. This is yellow is your standard data path today. Green is your enhanced data path. And you see almost 3 to 4 times more efficient CPU usage when you go with the enhanced data path standard mode. Right? Like instead of 1.21 throughput, like for example, with 1518, you're looking at almost 4 gig throughput per core with the enhanced data path standard mode. So those are some of the, again, from enterprise workload perspective, those are some of the metrics, the results that we've been seeing. The more edges you have, some of our customers, 1 edge per node is not very common, unless your hosts are really small and so on. Generally, you have more than one, 4, 5, 6, whatever, right? And once you get to those numbers, you're basically looking at full line rate throughput. Our issue has always been, it was not the VM edge that had a problem with the performance, but it had to do with the ESXi layer. And this stack is actually helping improve the ESXi layer, so you're taking that out as a bottleneck, basically. Okay. Demo, a quick demo. So this is with 700 byte packets. What I have is 2 systems. One system has all the package in, and then the other system has an edge with basically 16 cores. This is a Excel edge VM, as you can see here. And what I've done is just taking a brief look at what I was showing you earlier. How do you confirm whether this particular ESXi host has the enhanced data path standard enabled, right? In this case, if I look at VMNIC 5 and 4, which is, in my case, in this testbed, they are Mellanox based, you can look at the ENS capability, whether it is driven in the sense whether it is enabled, and also whether interrupt, that is the enhanced data path standard mode, is capable, and whether it is enabled, and so on. By the way, just one comment on that. Almost every NIC card out there should be able to support this. There's very few exceptions, so take a look at that. I love ESX top. This is the easiest way to figure out what's going on with your network. ESX top and press N, and you get your stats. Right now, there's nothing going on, so the numbers are closer to 0. And this is from the edge data path stats to look at how the packets look like on the edge. Let me go ahead and start packet gen. And it takes a little bit of time to ramp up the packet gen. And packet gen is a DPTK-based tool to just blast packets. And once it ramps up, that's about a 7 million number. This is with 700 byte packet size, right? And if you have taken pictures of the actual results, you would find they're very conservative. What I've shown you on the charts, right? Like what we actually see here is that is your transmit side. That's about 7 million, like after the edge has processed the packets, right? 7.5 million packets per second. That's going through that VMNIC 5. That column is packet transmitted. The second column is the MB. You have the packets received. Of course, if you're transmitting, you're actually receiving that much from the host too, right? And those who are familiar, that's the 700 bytes that you see. And if you look at the distribution, this is on the edge side, how those are distributed across too. One last thing, you can also look at the CPU utilization from the system itself if you go under the nodes, right? And monitor. At this point, the edge is only 40% used. It's not like really stressed out too. By the way, you need to refresh it to get to that metric. Okay. With that short demo, a few more things and we'll close. Monitoring. There are 5 different ways to monitor. Some of them are on demand, in the sense when I say on demand, what I mean is when I run this command, I get the data at that point. And some of these are not on demand. They are more, they are stored results and they are refreshed every 5 minutes. So when the NSX UI that I just showed you, where the CPU utilization of the edge was at 40%, that's actually, it's not a live data, it's captured every 5 minutes. So within those 5 minutes, if you keep pinging it like 10 times, you'll get the same number. But if you have your monitoring system that's not doing that, it captures every 5 or 10 minutes, you get the actual usage during that period. And then the API actually allows you to go both 5-minute intervals and also, if you want it, it can go on demand too. NSX CLI, if you're going on the host and running it, of course, it's on demand all the time. ESX, this is the one that I like. This is the easiest one. It's on demand too. Of course, it's not like real monitoring. When you're troubleshooting, that is where you go to that. And NetStats, I don't know. How many of you are familiar with NetStats? Okay, have used NetStats. Okay, are using NetStats for monitoring. Oh, I'm surprised. Okay, so some folks do use this. It gives you a lot of different details and data. Let's quickly go through some of these. The UI, we've just seen this. This is for the transport node, the different metrics that you can see. But let's look at the API side. On the API side, you get 2 options. You can go either the monitor route or you go the debug route. Debug is, of course, right, like at troubleshooting time. You don't want to be running this all the time for your monitoring stuff. In most cases, 5-minute monitoring should be okay, unless you're trying to troubleshoot something, in which case you go the debug route and keep getting that data on a constant basis. And the result is the same, but the resolution is different between these 2. NSX CLI or NSX DP CLI, if you want to go straight to that too, right? Is another way to get some data, but this is again like on demand. You get the data as it is at that point of time. This is my favorite, like I said, multiple times today. Probably the first thing that you want to look at, like if you're hitting some issues, is I won't call out everything, but it actually calls both the packet per second TX, that is transmit and receive, RX, and also MB that it is observing, what is the packet size that is being observed, both receive and transmit, and also drop percent. So it basically captures everything. Again, this is one of those reference slides if you ever need to use it too. Also, you can look at the compute side and see if something is getting pegged at 100%. That's also a sign of some issues or problem. But a better way to look at CPU usage is the net stats. In this case, I'm calling out netstats with very simple CPU utilization, but netstats can come back with histograms and whatnot, so you can really dig into it in terms of like trying to understand what's going on with your network. Of course, for monitoring purposes, the biggest piece that some customers, right, like if they're hitting issues, like you don't really need to go to this level, but if you want to, is basically looking at the used percent, as you can see here. For standard data path today, we have two threads. One is called the pole world threads, and the other one is the net world threads. And these are the ones that are allocated for receiving and transmitting. So you can look at those and like, for example, on the used side here, you can see one of those is at 99% usage and so on, right? So you can make a judgment in terms of what you want to do with that. So enhanced data path standard, instead of using two different threads, we use the same ENS network thread. And based on whether it is an even numbered or whether it is an odd numbered instance, you can figure out whether it is the receive thread or whether it is the transmit thread. And again, you get the usage here. And what people do is monitor this usage to confirm what's going on with their systems. Okay, we're almost close to end here. The smart NICs. How many of you have smart NICs in your infra today? Like you bought? Okay. How many of you are thinking of it? Thinking of it. Okay, okay. All right. So just a quick overview kind of thing. Some of these definitions are not still clear, so probably this will help. One of the things that I kept talking about is interrupt-driven versus dedicated allocation of cores. What does it mean to be interrupt-driven, enhanced data path standard, and enhanced data path performance? What is the difference between these two, right? And this goes back to the telco question too. So in an interrupt-driven mode, all of the cores are available, or threads, if it is hyperthreading enabled, they're available for both your workload and also for your network processing. And this is a good thing, because you don't want to basically capture some of the threads just for network processing and not make them available for your workload, right? So this is the advantage of having it in an interrupt-driven mode. Now, dedicated mode, this is the enhanced data path performance mode, which is what you would look at from the telco side and so on, right? In this particular case, what happens is you take not just a thread, but the entire core, and you say, this is for my packet processing alone. And the problem with this is you need to know how many you need, because if you under provision, you may drop some. If you over provision, you don't have ports for your workload. So this is a balance that you have to really figure out. And the folks, like a normal enterprise customer, most of the customers that I've come across, if I ask them, okay, what is your traffic pattern look like, right? You have no clue. Okay, VRNI, you get some insights and so on, right? But you don't really know, like especially coming from network side, what applications are actually running. So it's very difficult to figure out, okay, what do I need to provision here? But for some customers, that's not, like, I mean, with the telcos or certain very niche applications, they know exactly what's going on. In those cases, they can figure out what to do with this. Now, the third, so there's a risk of, over or under assignment, of course. The third mode is the offloaded mode. Here, what we're doing is all of the processing is offloaded to the NIC card. And so all of your CPU cores are available for packet processing. And you need to kind of like figure out whether this is the path you go in terms of like, how many cores you have and so on and so forth, right? So that's the DPU case. And the way this works is on the DPU, you have ESXi, a lighter ESXi installed on the DPU. And when packets show up, right, you go through this, let me build this up. When a packet shows up, If it's not in this, what you call the programmable accelerator, it goes to your flow cache on your ARM cores, and processing goes through that slow path. And once that's done, you program the accelerator. And then once if you really want to take advantage of the DPUs, you don't want to be leveraging the ARM cores. You want to be on this accelerator side, even though there may be a few use cases where you could still gain some benefit, but you want to stay on the accelerator side. And the entire thing is offloaded in the sense like you still get that benefit of moving everything down to the CPUs, but that portion is the accelerated portion. And all of the networking functions today are accelerated. On the security side too, there's a few that are accelerated, and there's a few that may actually leverage the ARM cores. Now, on the ESXi layer, right, you still have the ESXi on your host, and there is a common lifecycle management for both on the DPU and also on the ESXi host. They are basically programmed the same way, or the OS is loaded the same way. And within the ESXi layer, you have two modes for operating the DPUs. One mode allows you almost a SRIOV style, where you're bypassing most of the stack. You go from the DPU directly to your VM. That is what we call the UPTV mode 2 mode, where your CPU usage is very light. But of course, you need to make sure that your DPU has enough paths, enough VIFs to enable like however number of VMs that you want to allocate, right? And also, those VMs need to have memory reserved. So it depends on how much memory you have to. Another mode to go with, you can still reap some of the benefits, is to go with the emulated mode, where you can have multiple of these VMs running off of a single layer. Of course, there's some CPU cost, but it's not, I mean, it's negligible. It's not the same as when you have the PNIC. What we've done with 5.2 and 4.2 NSX, right? Now we have two DPUs, support for two DPUs. And again, the lifecycle management for both the DPUs is common, the same thing. Single lifecycle management, and you get a better, higher, either you choose, because it's two different distinct ESX nodes here on those DPUs per DPU, right? You get to choose whether you want to go with a high availability mode, where you're basically leveraging only one DPU for your traffic, and the other one is a standby. One of the use cases is like you can upgrade the standby and move over to the standby and so on based on need, right? The other mode is to go with two different VDSs because those are two distinct entities, right? And then leverage, again, from performance point of view, in this case, you maximize the throughput available for both the DPUs. Yeah, you could be running different workloads too on those two DPUs. Okay, I told you you would recognize one more slide. Maybe if you've seen the previous sessions, you would recognize this. But in conclusion, right, there's a few things to take a look at. I love this analogy. Like, I mean, you're looking at performance. You want to get the best performance out of your box. Then you start looking at the hardware, right? Like you start looking at, just like a fast car, you look at the NIC cards, you look at the CPUs, you look at the RAM, what you have allocated, how you have carved it out. You look at the configuration, what offloads are you using if you are using the standard data path. You go enhance standard data path standard mode, then you don't have to worry about config much in terms of like tuning, okay? Because it's tuned right from get-go. Queuing, and then this is key, VMware Compatibility I/O. How many of you are familiar with this tool? Okay. Please use this tool, okay? This avoids a lot. A bunch of cases can be solved just by going to this tool and figuring out the driver firmware revisions. Throughput versus latency, or both. And finally, what stack do you choose? And basically, now that you have enhanced data path standard, like you could also scale this out, more CPUs and so on too. Okay, 45 seconds more for any follow-up questions. All good? Oh, wow, cool, awesome, okay. If no other questions, I think we can call it. And some of your, I guess you have to catch a flight or something too, I guess. But if no other questions, okay, we're done. Cool. So.